Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of Electronics and Communication Engineering at MLR Institute of Technology. So today I'm going to explain the instruction set of 8086 microprocessor arithmetic operations. This video is the part of series microprocessors and microcontrollers. The first part of this instruction set have been already explained in the previous video. Do watch that video. So in this video, I'm going to explain what are the arithmetic instructions present in 8086 microprocessor. So here the overview of the topics is increment and decrement operations, ASCII adjustment instructions and decimal adjustment instructions present in 8086. So the first one is, while coming to the arithmetical operations, we have already known the arithmetical operations are addition, subtraction, multiplication and division. Along with these arithmetical operations, there are some increment and decrement operations and how to find out the adjustments after performing the ASCII and decimal adjustments instructions. So coming to the arithmetic operations, in that first one is addition operation. Here addition operation is used to add two numbers where the numbers can be present in memory or can be directly mentioned. Here the results always be stored in the destination operand. Like if we are writing add AX comma BX, as you all know that this is the register addressing mode. Here the operands, this is the destination operand and this one is the source operand. So here the output will be stored in the accumulator. The output always will be stored in the destination operand, whether it is a memory or direct register, but the destination operand should not be the immediate value. Raw data shouldn't be given as the destination register because the destination operand need to store the output. Here the operation will be performed like this. The data present in AX will be added to the data present in the register BX and this output will be stored in the AX register according to this instruction. So always the output will be stored in the destination operand, whether it is a memory or it is a register. So here while performing these addition operations, memory to memory addition will not be supportable in 8086 microprocessor. Like we can't give like this. So if we are considering 1234 is an address of a memory and the second address is 4531, the value present in these two memory addresses cannot be performed. It will give illegal operand because there is no such instruction to perform memory to memory additions, or any operations cannot be performed directly in the memory to memory operations. So the contents of the segment registers cannot be added in this instruction. So the segment registers contents will not be added. This instruction is also not going to present in the 8086 microprocessor. And the conditional codes which we are having, zero flag, sign flag, parity flag, all these conditional codes in the flag register may be affected after performing such type of instructions. So here you can directly, here we can write more number of instructions. Like if we are considering move AL comma 34H, here I was giving hexadecimal number as an example and I was giving the data in the BL like this. So I can add here. What will be the operation? The output will be stored in AL register and the operation AL plus BL will be performed. Here if we are considering AL value is 34 and BL value is 12. So this will be perform addition and the output will be stored in the register AL. So after performing these three instructions, the output will be present in the AL register and the output will be 46. So here I was taking, I took the normal numbers which can be represented, then these numbers can be same in decimal part and hexadecimal part. If I was taking the numbers like example 3, 9 and 1, 2. Now what will be the output? In decimal part we actually thought 9 plus 2 is 11, so 1 will be here, 1 will be taken as a carry? No. In such cases, the operations will always be performed in the hexadecimal number, because I have given the hexadecimal number here. 34H. H represents the hexadecimal number. So while we are doing these operations, 9 plus 2, which is nothing but 11. So how we will represent 11 in hexadecimal number? So we will represent by the alphabet B. So here the possible output will be B, and 3 plus 1, 4. This is the output present in the AL register after performing these 3 instructions. So this is all about the addition operation. Here, if we are having, if the lower nibble of data is having any carry to generated after performing any operations, those carry represents as a auxiliary carry in the flag register, one of the condition codes of flag register. So it will be set to 1. And if we are having carry after 8-bit, after 16-bit addition, so such carries are considered as a carry flag. Carry flag will be enabled as the condition code flag. So if we are having more number of value than 16-bit data, then overflow flag will be enabled. Even parity, odd parity, those all are the conditional codes. In this arithmetical operations, these codes may be affected. So performing the operations. Next, coming to the instruction ADC. ADC is also similar like add instruction, but the difference is in add instruction we won't add carry flag. So we won't consider carry flag. If we are performing any operations by using ADC, then after performing addition, the carry flag will be added to the output and the total output will be generated as ADC. Suppose we are using ADC AL comma BL, then the data present in as the output will be present in the AL, and the AL will contain the data AL plus BL plus carry flag. If any carry will be there, that will be added along with AL and BL contents. So this is the difference between add and ADC operations. Next instruction is increment instruction. Such type of instructions will increment the data or the value present in the registers by 1. In such type of instructions, we can't give immediate data as a operand. So if we want to perform any operations like increment operation as well as decrement operation on immediate data, it shouldn't be allowed, because immediate data should not be the content of this type of instructions. Immediate data cannot be the operand of these instructions. In these instructions, all the conditional code flags can be affected by these instructions except carry flag. Carry flag will not be affected in such type of instructions. Suppose let us consider one instruction. If I was move AL comma 1 to H. So I was placing 1 to H data into AL register. After this, if I was writing increment AL, the output after performing this instruction will be AL equals to 12 plus 1, which is nothing but 13. In such type of instructions, carry flag will not be affected. Other conditional flags can be affected. So coming to the next operation, which is exact replica of the increment instruction. So this instruction is decrement instruction. So in this instruction also, the data present in register or memory location can be decremented by 1. So such type of instructions, carry flag will not be affected. Other conditional flags can be affected, depends upon the instruction. So here the immediate data shouldn't be placed as an operand in the instruction itself. Suppose if I was taking move BX register as 1, 2, 3, 4H. Now if I was performing decrement operation on BX, so the output will be the data present in the BX register will be subtracted by 1 and the output will be 1, 2, 3, 3H. So this is the output present in the BX register after performing the decrement operation. Next, coming to the operations, subtraction operation, and SBB is the operation depends upon the subtraction with borrows. These two operations are similar like addition and addition with carry. Here subtraction and subtraction with carry. So if we are performing subtraction operation, suppose take move AX comma 1, 2, 3, 4H and you can directly write the subtract operation like subtract AX, 1, 2, 1, 1H. So what will be the output after this instruction? So basically here we are performing the operation like the output will be stored always as in the destination operand. In this particular instruction, the destination operand is the register AX. So AX register will hold the output after executing this instruction. So what will be the output present in the AX? Will AX minus the source operand. Here the source operand I have given as 1211H. So in this particular type of instructions, we can mention the source operand as a immediate data, but destination operand shouldn't be the immediate data. The destination operand should always be the register or memory. So here what will be the operation performed here is, so 1, 2, 3, 4. The data present in AX register will be subtracted 11H. So what will be the possible output? So 0023H will be the output stored after performing subtraction instruction in this particular case. So AX will hold the data 0023H value. So coming to the SBB operation, instead of writing SUB here, if you are writing SBB here, then if any borrow is generated, that borrow which represent as the carry flag will represents this borrow. So if carry flag is enabled, then the carry flag will be subtracted from this output. After performing here, the carry also subtracted from the output. So here also the result will always stored in the destination operand, and memory to memory subtractions will not be performed. Memory to memory subtractions will also not be performed. And here also conditional code flags may affect after these instructions, or in all the arithmetical instructions, the conditional codes may be changed. So coming to the next instruction, multiplication instruction. Here in multiplication instruction, here MUL represents the unsigned multiplication, while IMUL represents the signed multiplication. So here the example is mul bx. So actually in the previous where addition and subtraction instructions, we have mentioned the source operand and the destination operand. But in case of multiplication and division instructions, the source operand and destination operand will not be there in the instruction itself, because in multiplication and division operations, the source multiplication and division operations, the destination register always be the AX register. So if we are performing 16-bit data, then the destination register will be the AX register. If we are performing 8-bit data, then the destination will always be the AL register. So in this particular instruction, what will be happen means, after performing this multiplication operation, the output will always be stored in AX register, because here we are performing 16-bit operations, and the output is the AX contents of the AX register will be multiplied with the contents of the BX register. So let us consider one example. If move AX 01H and move AL is enough to hold 8-bit data, so I was changing it as AL. And if I was taking BL as 04H, now if I perform multiplication operation, then you just mention BL. So after this, in this particular instruction, AL is loaded with 01H value, and this value will be loaded with 04H. After performing this instruction, the output will be stored in AX as 01 into 04, which will be 04H. Output will always be stored in the AL destination register. If we are performing any 16-bit operations, like if I was performing any 16-bit operations, if we are multiplying 16-bit data with the 16-bit data, there is high possibility of getting more number of outputs, more bits of outputs. Like if we are multiplying 16-bit with 16-bit data, then we may have the chance of getting 32-bit data. Now the problem arises that if we are having 32-bit data, the total 8086 microprocessor is having only 16-bit registers. So now Other 16-bit data, where can we find this other 16-bit data? In such type of instructions, the combination of DX register with ALX register will hold the total 32 bits of output. So the lower 16 word will be stored in AX register and the higher 16 bit will be stored in the DX register. So these two registers, DX and AX register, will hold the total outputs. Next, coming to the division operation. Here also there are two types of division operations, which is div, normal unsigned division will be performed, and here IDiv, signed division will be performed. Here also for division operations we are getting two outputs. One is coefficient and another is remainder. So the main output will be the coefficient. This output will be stored in the AX register and the remainder will be stored in the DX register. So in such type of instructions like multiplication and division, these two instructions, the output will be stored in two registers, AX and DX registers. So coming to here how division operation will perform. Here also division operation also, the destination register always be the AL. If we are using 16-bit data, then the divisor will be always be stored in AL register. Here after performing div BX register, what it will get? The AX register will hold the value by AX divided by DX. This will be the output stored in the AX register. Next, coming to the comparison operation. So comparison operation is used to compare the source operand with the destination operand. Actually here the source operand, the data present, it subtracts the source operand from the destination operand. Suppose if I was writing compare AX comma BX. So in this particular case, here the BX is the source operand and AX is the destination operand. So source operand is subtracted from the destination operand, like AX minus BX. This operation will be performed. But in this comparison operation, the output will not be stored in any register because it just enables the flags. If after performing the comparison operation, if the two data present in both operands are same, then zero flag is set. So we can say after checking the zero flag, we can able to find that the two operands are equal. If the source operand is greater than the destination operand, then carry flag is set to 1. So if the destination operand is greater than the source operand, then we can say we can check the carry flag is set to carry flag is reset. So in these three conditions we can find. So while comparing the two operands, either the two operands will be equal or one operand is greater than the operand, or that same operand will be less than the second operand. So in these three outputs, the conditions will be checked by the flag register. So if the two operands are equal, zero flag is set. If the destination is greater than the source operand, then flag is carry flag is reset, and the vice versa, carry flag is set. So in this particular comparison operation, the output will not be stored in any register. We need to check the flag registers for corresponding outputs. So coming to the next instructions, there are 4 instructions: AAA, AAS, AAM and AAD. These 4 instructions are represented as a ASCII adjust after addition. This AAA instruction is used to adjust the value if we are performing this particularly this instruction is used after only performing addition operation. If we are adding 2 ASCII represented numbers, suppose here the number which here present in the AL register is 34, which is the ASCII representation of number 4. So what is the ASCII representation of 4? Here 34. And the ASCII representation of 8 will be the 38. If we are performing addition between the ASCII numbers, then the output will also be in the ASCII representation. But if we want the output in the format of a binary coded decimal, then we can go for this AAA instruction. So this instruction particularly targets only AL register. Accumulator lower byte register will be taken, and the data present in that particular register will be converted into the corresponding binary coded decimal. So after performing ASCII additions, we can use this instruction to get the binary coded decimal as the output. Next, coming to the AAS instruction. In this particular type of instruction, after performing subtraction operations, we will use AAS instruction. So to find out the binary coded decimal value for the subtracted result. So here AAM and AAD instructions are there. This instruction is the ASCII just after multiplication, and AAD, this is the instruction which performs the adjustment before performing the division operation. So this is the instruction ASCII adjusted before division. So as I told that microprocessor works on hexadecimal numbers. So these are the instructions present in the arithmetical set of 8086 microprocessor. So until now I have discussed the arithmetical operations like addition, addition with carry, subtraction, subtraction with borrow, division, multiplication, signed division, unsigned division, multiplication, signed multiplication, unsigned multiplication, and what are the operations we can perform using arithmetical instructions. Thank you.